So if we want to know why K means converges, we can intuitively think about it this way. Every time we make an update to either Ci or mu k, we're finding a new value for these parameters that decreases L compared to the previous value for those parameters. So for a particular Ci, when we update it, we have found a new value that makes L less than it was previously. In that sense, L is monotonically decreasing. Every update we make by the design of the algorithm is finding a new value of the parameters such that L is less than it was previously. Also, if we look at the objective, it's bounded below by 0. So it can't be, just by construction of the objective, if you look at, we're summing squared distances, and so that sum has to be a positive number. It can't be a negative number, which means that there's a lower bound, and so L has to converge at some point, but probably not to 0. So there's more to it than that, but we won't go into more details about the proof of convergence. But when one way we can prove that it has converged is if C stops changing, then mu is not going to change. And if mu is not going to change, C is not going to change. So once these values stop changing, we know that we've converged. We can't improve it anymore. However, again, because this function L is not convex in C and mu, maybe it's convex in one of them but not in the other, but it's not convex in both C and mu together, what we've converged to is a local optimal solution, not the global optimal. So in practice, what non-convexity means, when you hear non-convex, you should think that what that's telling you is that different initializations will converge to different final solutions. If you hear convex, what that means is any initialization will always converge to exactly the same solution, and it will also be the best solution. Non-convex means it'll converge to different solutions, and they'll only be locally optimal. In practice, what is observed, however, is that the quality of the solutions will be similar. You won't necessarily converge to a solution that's much worse than another. That's an empirical observation, but there are no guarantees. And so if we want to feel more confident about the quality of our solution, a computationally intensive way, but a way nonetheless, is to simply run the algorithm multiple times from multiple different initializations and then pick the objective with the lowest value. Because if it's the same model but with different initializations, then if you have two local optimal solutions, you can definitively say that one is better than the other if the objective is less for one than it is for the other. Another practical issue with k-means is selecting k. So we don't know in practice how many clusters we should use. We can't necessarily visualize the data like we did in the previous slides. And so selecting k is a tricky thing. Also important to notice is that we can't compare k-means objective functions across different settings of k. For the same setting of k, we can compare different runs of the k-means objective function. But for different settings of k, we can't compare them because they're different models. We can't directly compare them. And in particular, as k increases, this thing is going to always decrease. So as k gets bigger and bigger, we're always going to decrease this thing more and more. For example, if you want a quick way of thinking about it, if we set k to be equal to n, so we set the number of clusters to be equal to the number of data points, and then we let the centroid for the kth cluster be equal to the kth data point, then we can make this thing equal 0. That's the optimal. It can't be less than 0. And so we've perfectly clustered all our data point by putting each data point in its own unique individual cluster. However, I don't need to convince you that that's not a desirable thing. We've kind of defeated the purpose of modeling, which is to simplify the data and summarize it in some way. So how can we learn K? There's multiple methods. One thing, so a few of them are a bit hand-wavy, but one thing is we can use our advanced knowledge about the problem. So for example, if you want to split a set of tasks across K different people, then you know that there are going to be K different clusters that you need to set. Another thing we can do is look at the relative decrease of the objective function. And so even though as K increases, L is going to always be decreasing because we're always going to be able to cluster the data in a way that these squared distances are going to be less and less and less. We're always going to get clusters so that the data is closer to the centroid that it's assigned to. Relatively speaking, however, if we think of K star as being the ideal number of clusters in our data, then, and this is simply a heuristic argument, but then what we can think of is that as we increase K for K less than K star, so K star, for example, is 10, and K is now increasing from 3 to 4 to 5 and so on, we should see much, much more improvement in our objective function as we let K increase to K star. So adding that extra cluster should really help cut this thing down quite a bit. But then, once we start going past K star and we start over-clustering our data, we should see that the marginal decrease in this objective is getting less and less. So after we increase the number of clusters to be more than what is necessary according to the data, the improvement, we get diminishing returns in a way. So you could imagine it to look like this. So here's L, and here's K, and maybe here's K star. So we should see it in this regime really decreasing quickly, and then suddenly maybe it starts flattening out. So that's a heuristic thing that you can try. Another thing, and one of the reasons why K Means is so popular, is that it's often used as a pre-processing step as part of a larger application. So for example, if we want to take our continuous data and we don't want to put a continuous model of it, we don't want to learn a continuous model of it, we maybe want to first discretize the data. So we take each point, xi, and instead of learning a continuous distribution on that, we assign it to a cluster, and now each point is represented by an index between 1 and K. So we've discretized the data. Then we can learn a discrete model. Oftentimes, that's something that we'll want to do. In that case, that discrete model, and so this is again a bit hand-wavy, is being used for its own application. And so we can use whatever we're trying to use that our larger application for. That might have its own quality measures, and we can then, for multiple discretizations, multiple values of K, see how well we perform on some other task we're trying to do. Also, there are more advanced modeling techniques such as Bayesian nonparametrics, but we won't discuss that in this class.